All right, here we are with lecture example 1.1.8, solve the initial value problem. I had it spelled incorrectly there. Anyhow, the differential equation we're handed here is y double prime equals x e to the 2x, and we are given two initial values, y of 0 equaling -1, and y prime at that very same x value of 0 is equal to 2. That x value of 0 is the initial time value. This is why it's called an initial value problem. If we were handed, for example, y of 0 is equal to -1 and y prime of 10 is equal to 2, that would be called a boundary value problem because you're considering two different points, x values. And technically, even that is slightly incorrect. To be a boundary value problem, you would prefer that you have y of, let's just say 0 is equal to -1, and y of 10, not y prime of 10, equaling some number. That would be called a boundary value problem. Not that big of a deal here. We're just dealing with initial value problems. So let's go ahead and figure this out. To find out what y is, we will have to take the antiderivative twice, right? Take the antiderivative of y double prime first to find y prime, and then do it again to find y. Now, I'm going to use a technique here that you may not be familiar with, but you should know that you are going to be using integration by parts here. I just happen to use a little table once my students get outside of Calc 2 to do my anti-differentiation when it comes to integration by parts. You choose the factor that you're going to choose to differentiate, and you'll choose your factor that will be integrated. So x will be the factor that I will differentiate, and e to the 2x will be the factor that I integrate. Now, if you differentiate x, you get 1. If you differentiate that again, you get 0. If you integrate e to the 2x, you get 1/2 e to the 2x. And I'm using a very large ink, or in other words, I am zoomed in way too much. If I integrate one more time, I will get 1/4 e to the 2x. If you haven't seen this table, it's a very cool way to do integration by parts. I do not like to teach this in my Calc 2 class because it's too much of a trick. I want students to know how to do integration by parts rather than just copy a table. However, now that I have this written down, I'm going to show you the cool little trick here. You're going to take this diagonal, take the product, and you're going to put a plus sign in front of that product. And you're going to take the next diagonal, take its product, and put a minus sign in front of that. It's sort of like if you've taken linear algebra, computing a determinant, where you have that sign chart over your matrix as you're computing cofactors and doing the cofactor expansion. All right, if you don't know what I just said, doesn't really matter. But what does matter is that you can find that y prime here is going to be the positive value of x times a 1/2 e to the 2x, and then minus a value of 1 times 1/4 e to the 2x. Now, I would probably like to just glue these things together and make it look a little bit better. There we go. Now you can see I have yet another antiderivative to go through. By the way, I should mention here, you have a constant of integration, and that's going to be very important. I'm going to call that C sub 1. That's critical for this course, right? We have this constant of integration after you do the first integral. Now the second integral, you get a second constant of integration. However, if you happen to know that y prime of a value is equal to a value, that's part of our initial condition, you can go ahead and substitute that in right now to find out what C sub 1 is. So let's go ahead and do that. Now, obviously, I didn't have to write out 1/2 times 0, e to the 0th, and all that fun stuff. I'm just doing that so you know what I'm plugging in, right? I'm plugging zeros in for x's and the 2 in for y prime. And here we go. We find out that C sub 1 is equal to 9/4. Now, I could have held off on that, but I didn't want to. I wanted to go ahead and compute that now, but you could have waited till the bitter end to compute that. You don't have to do it in the order that I do it. Now that I know what y prime is, well, my ultimate goal was to solve the initial value problem, and so that means I need to find out what y is, the original function, given these two initial points. So let's go ahead and do one more antiderivative, and we happen to know the antiderivative of 9/4. We know the antiderivative of e to the 2x. Those are the easy ones. But what about that x e to the 2x? Well, again, I kind of already have done it, haven't I? To compute the antiderivative of x e to the 2x, well, it's just this business here plus an additional constant of integration. So I'm going to go ahead and just copy my work above. Now, a couple things I want to mention here. First of all, when I found the antiderivative of y prime, remember, I already computed the antiderivative of x e to the 2x. So that's what this chunk is here. I had a 1/2 sitting out front, so that's where that 1/2 came from. Also, we computed the antiderivative of e to the 2x. Well, that's just 1/2 e to the 2x, and you're multiplying it by 1/4. That's where that negative 1/8 is. So that's okay. That should make sense to you. The other thing I want to mention here is just from your Calc 2 class. Remember, when you find the antiderivative, you get a constant of integration. Technically speaking, there is a constant of integration right here. I'm going to call it c sub 2 bar, because when we took the antiderivative of this, we found a constant of integration. In fact, each one of these, the antiderivative of negative 1/4 e to the 2x and the antiderivative of 9/4, they all produce constants of integration. However, you can just glue all those constants of integration together into one constant, which I shall call c sub 2. Even though you might say, wait a second, but the constant of integration from this group is being multiplied by half. That's fine. 1/2 times a constant is still just a random arbitrary constant. It's arbitrary until I go ahead and use my initial condition, that is. So let's clean this up first. I don't like to have parentheses in here, so let me clean this up. And I did a little bit of extra arithmetic in there to combine some terms, but that is our function y. Now remember, we still have a parameter, c sub 2 here, and that is because we have not used our final initial condition, which is y of 0 is negative 1. So let's go ahead and let the output be negative 1. And this time I went ahead and just looked wherever I had x's. I knew that I was plugging in 0, and so those disappeared. That wasn't a big deal. I'll add a 4th to both sides, and that looks about right to me. So let me go ahead and just box that up and go back to my function here and say, well, given these two initial conditions, y of 0 is equal to negative 1 and y prime of 0 is equal to 2, the function whose second derivative is equal to x e to the 2x, given those two initial conditions, is going to be the following. That's a pretty good looking function. I'm going to go ahead and highlight that. Now, just as a heads up, the family of solutions to this differential equations here is actually the family that looks as follows. The family has two parameters, two things that can be adjusted using dials. Now, those parameters will be locked down if somebody comes in the room and says, hey, I've got some initial conditions. Y of 0 is something and y of 10 is something, or y of 0 is something, y prime of 0 is something, or y of 1 is something and y of pi is something, whatever it may be. So as long as they give us two conditions, we can lock down the exact solution to this differential equation. And as was mentioned in class, there are an infinite number of solutions, as you can see by the parameters that we had a moment ago, to a differential equation. And by itself, any of those solutions are sufficient to respond with. So I could just say, well, you want a solution to the y double prime is equal to x e to the 2x? Sure, I'll give you one. It is 1/4 x e to the 2x minus 1/4 e to the 2x. And that's it. right? So in other words, I'm just saying if C1 and C2 are 0, well, that is technically a solution, right? You could plug that in. Just pretend as though this chunk right here doesn't exist. Plug that into your differential equation. What you have 1/4 x e to the 2x and minus 1/4 e to the 2x. Plug that into your differential equation. You will see that the left-hand side will become the right-hand side. It is actually true. So when you're not given an initial value problem, there's a lot of possible answers. There's an infinite number of possible answers you can give. But once somebody nails it down using an initial value problem, which is more realistic in the real world, then you will hammer down and find the exact function, the one function that yields those initial conditions. All right, that does it for this example.